Can you see it?
Okay, our next speaker is Jasper. Sorry, surname. Roosmale Nepveu. Okay, he will tell us about high order renormalizations in scalar effective theory. Let's go.
Thank you. Can you also see my mouse, by the way?
Yes, I can see that.
Okay, perfect. Thank you very much. So thank you to all the organizers for giving me this opportunity to talk about our work. This is work in collaboration with Weiguang, Franz, and Tom, and we hope to publish about it as soon as we can. So what we set out to do is we normalize the scalar effective field theory at higher order. So higher order meaning higher loop order and higher mass dimension. And we chose this toy model of the scalar theory because this allowed us to apply our methods at these higher orders. And then we can analyze the structures that we observe in the anomalous dimensions very well. And also we set out to study the basis dependence of the anomalous dimensions. And in particular, we're going to look at a special basis, which is the basis of conformal primaries. And we're going to observe some of the structures that appear there. So in this talk, I will first introduce this basis, the primaries. I'll introduce also quickly anomalous dimensions, but I hope you're familiar with this. And then I'll describe our main method that we use to obtain the counter terms. And from there, the anomalous dimensions, which is the R star operation. I will give the general form of our results, and then I will look to make it less abstract into one example, which is the anomalous dimension matrix at mass dimension 8. And also I'll make a change of basis on this matrix to show how this happens and to point out some structure that appears in the basis of the primaries. But first of all, so what is the theory that we're looking at? We're looking at the massless scalar effective field theory, both the real and the complex theory. So the renormalizable part should be very familiar. It's just 5 to the 4. We have no mass and we have no phi cubed. So in particular, we won't have any odd mass dimensions appearing in the EFT expansion. And to this renormalizable part, we add higher dimensional operators. For example, what you can add is 5 to the 6 operator with the simple Feynman rule, just 1. Or you could add an operator with 4 fields and 4 derivatives, like I showed here, with a slightly more complicated Feynman rule. So the question is, which operators do you need to add so that you have no redundancies between the operators, no relations between them, but you can cover all the physics. So this is your choice of operator basis. And if you deal with this question systematically, you are pointed to the basis of conformal primaries. So this is done in the literature that I cite here. And in particular, also note Tom Media's talk yesterday at this workshop. So what is this basis? It's given by every operator, where I see operators as their Feynman rules, that are annihilated by this operator K, where K is the generator of special conformal transformations. So already the fact that this gives the right number of operators to form a basis is rather special. So just to give you an example to see what it looks like, what kind of operators look like, this is already quite unnecessarily complicated example at mass dimension 10. So we have 4 fields and 6 derivatives, and an inner combination of these terms is annihilated. So its Feynman rule is annihilated by this K. On the second line, I show exactly the same as the first line, but just in a way to visualize more easily. So every field I represent by a red dot here. And then since derivatives are contracted in pairs, they can be represented by lines between the fields, where the endpoints of the line tells you where the derivatives act. So this is visualizing more easily these operators. So the general approach to find a conformal primary is to start with your most general Feynman rule with 3 parameters, and then impose, find those parameters that make the combination annihilated by K. So for this, you need to know what is your most general Feynman rule, right? So Feynman rules, they know about momentum conservation. So this is something that you can already impose. So for the keen eye, you'll see that there are no self loops on these graphs, meaning there's no d squared acting on a single phi. That is because using momentum conservation, we do not have to consider these. So because I'll come back to this later in one slide, these 6 operators, they span your most general Feynman rule. That is the point I wanted to make. So another reason why this basis is special is for the behavior of the primaries under or in the phase space integral. So in the CFT literature, the object of interest is really 2-point functions. Here, by unitarity, these are related by such a cut in the 2-point function. So this gives you the phase space integral between these insertions of operators. So what is interesting for the primaries is that the primaries under this phase space integral are orthogonal to, first of all, operators with a d squared phi inside. So this is, I have to admit, rather trivial because d squared phi gives rise to p squared, and p squared gives 0 in the phase space because it's on shell. The second line is non-trivial because this inflowing momentum p here is not 0 in the way we define the integral. So the fact that primaries are orthogonal to such operators has content, and I will use this statement later as well. So I wanted to include both of these because this, only for conceptual reasons, it's conceptually nice that the primaries under this phase space integral, they are really orthogonal. They're isolated from these redundant operators, where redundancies in your effective field theory, they're related to on-shellness or equations of motion, so this d squared phi, and momentum conservation, so this overall p. So that's why I wanted to include both. So as I said, we will study part of this behavior of this basis through the anomalous dimensions, because anomalous dimensions are basis dependent. So let me quickly introduce to you what are anomalous dimensions. They encode the scale dependence of the couplings. So in dimensional regularizations, coupling becomes scale dependence. It's this dependence on the scale mu here. This is encoded in, first of all, matrices that mix couplings of the same mass dimension. And then in general, we also have tensors that will mix couplings of other mass dimensions, in particular products of these couplings. But for this talk, I will only focus on these matrices. So for example, mass dimension 8, the scale dependence of a single coupling mixes the other mass dimension 8 couplings, and also it mixes the mass dimension 6 squared. And the anomalous dimensions, they are determined from the counter term, which we determine in the MS scheme. And so on the next slide, I will show you our method that we apply, how to calculate the counter term. So this is the R star operation. What it does is it recursively subtracts both UV and infrared subdivergences from your correlators, from your diagrams. And after doing this, after subtracting your subdivergences, what remains is an overall divergence, which is local, meaning it is polynomial in the momenta. And because it's polynomial, that's why it's possible to find a counter term to subtract this divergence. Since it's a polynomial in the momenta, what you can do is you can Taylor expand the counter term. So here, Z corresponds to the counter term operation applied to some diagram. And this first statement is just the fact that because it's a polynomial in the momenta, we can Taylor expand with respect to this momenta. The statement, the non-trivial equality, is the second one here, where we interchange the order of the counter term operation with the Taylor expansion. So the claim is that the counter term of the diagram that we have Taylor expanded will be the same as the Taylor expansion of the counter term, or basically the same as the counter term. And in general, this is not true, because you have to realize what does the Taylor expansion do? It takes derivatives with respect to external momenta, and it sets these to 0. And since your external momenta, we are working off shell here, since your external momenta regulate infrared divergences, this procedure generally introduces infrared divergences. However, R star is so powerful because it is able to recognize and subtract those infrared subdivergences. So this is why, if you apply R star, such a procedure is allowed, and you will still get the correct counter terms. In a similar way, we are allowed to do a procedure called infrared rearrangement. So what this does is for logarithmically divergent diagrams. So importantly, first we can Taylor expand diagrams with high degree of divergence to logarithmically degree of divergence. And then for those diagrams with a logarithmic degree of divergence, we can change the way these external momenta flow into the diagrams and without changing the counter term. So that's shown here. The counter term for such a diagram is the same as for the diagrams with other flows of external momenta. And in this way, we can greatly simplify the calculations of such diagrams. Also, as before, this playing around with the external parameters, which are infrared parameters, they typically introduce infrared divergences, but these are subtracted by the R star operation. All right, so next, since we renormalize off-shell Green's functions, the counter term that come as outputs of our calculations, they're typically not in the physical basis, but they're also outside this physical basis, because off-shell Green functions are more broad than on-shell S matrix elements. So as counter terms, you will need the full set of operators that are independent on integration by parts. So you need the most general Feynman rule, access to all the general Feynman rules for counter terms. So these are the 6 operators that we saw before when I showed you the primary. So this is just an example at mass dimension 10. So in general, you will have 6 counter term vertices, and this means that if you go to higher loops, typically you will have many vertices arising with different counter terms. But importantly, in R star, that's due to this recursive nature, you do not have to include your counter terms as input in your calculation, because R star recognizes by itself the subdivergences and subtracts these. So you don't have to subtract subdivergences by inserting by hand your counter term vertices. This is done automatically. So the conclusion is, as input, you do not have to include this larger basis. As input, you can just calculate the physical basis. And as output, then you do get counter terms that are proportional to all of these. And you need to go using theory definitions to a physical basis. So this R star operation was implemented in Maple and Form, and it also makes use of the Forcer program. So let's jump to the results that we have obtained using this method. So first of all, how far did we go? At mass dimension 4, we have confirmed existing results up to 5 loop order. And then for the real and the complex scalar. At mass dimension 6, we went to 5 loops for the real scalar, and we went up to mass dimension 12 for the real scalar at 1 loop. For the complex scalar, we went up to mass dimension 10 at 2 loops. So the general structure that we observed in the anomalous dimensions, this is for the complex scalar at general mass dimension. I've here schematically given you in the next slide, I'll give an example, but here's the general form of these matrices. So in the upper triangle, you find entries that correspond to mixing of a smaller operator into a larger operator. So an operator with less fields into more fields. On the lower triangle, you find entries that correspond to mixing of larger operators into smaller operators. And on the diagonal, there's mixing between operators with the same number of fields. So what we find, interestingly, is a 1 loop 0 here in the mixing of an n-2 point operator into an n point operator. So no derivatives and 2 derivatives. And this is 0 only in the basis of primaries. In another basis, it's not 0. However, unfortunately, it's not true that at 1 loop, the whole upper triangle becomes 0 in this basis, because in general, these purple entries are not 0. On the lower triangle, we confirm expected zeros from this reference here, up to n-n loop order. But importantly, we find a 0 which goes beyond this result here at 3 loops, which is unexpected, because the diagrams that contribute, they are not only non-zero, but only as a combination, those diagrams will be proportional to p squared, so that the effect can be removed by Fourier definitions. But before doing the calculation, it is really unclear where this comes from. So that's an interesting result. And it's also particular only of this mixing between the highest point operators, so the operators with the most fields. Now, finally, on the diagonal, we have this submatrix of operators with the same number of fields, which from this literature in conformal field theory is, it follows that this will be symmetric at 1 loop for an orthonormal choice of primaries, where orthonormal refers to this phase space integral. And this we have confirmed in all the results that we have calculated. So just to give you an example to show you with the actual numbers, the results. So here we have the 1 loop zeros. So this is a complex scalar at mass dimension 8. We have an 8-point operator, a 6-point operator, and 2 4-point operators. We have this 0 that occurs only in the basis of primaries. But these entries, as I said, they are non-zero. So to make a more general conclusion about primaries here is not possible, because it would mean that these entries would also be 0. As I said here, these zeros were predicted in previous literature, and we confirmed them, where the 2 loop results here are slightly non-trivial because there are non-zero diagrams that contribute to these entries, but after field redefinitions, this will become 0. And as I said, there's 3 loop 0 that goes beyond the existing results here. And a similar entry here is non-zero. So again, this is particular only of the mixing of the 2 operators with the highest number of fields at a particular mass dimension. So for the rest of this talk, I want to zoom into this submatrix of the 2 primary operators of the same number of fields. And I will copy this matrix at 1 loop to this slide. So this matrix this result is given for just a particular choice of 2 independent primaries, but you can make any choice you like. So in particular, you can take linear combinations of these primary operators, which is what I've done here. And in particular, I've chosen the linear combinations such that the phase space integral of these operators, of the 2 different operators, is 0. So they are orthogonal, but the phase space integrals of the operators squared is the same. So they are normalized in this sense. So here, yeah, these numbers are not too important, but I think it's interesting to see sort of what it looks like. So you have sines. This is for any theta. This basis is orthonormal. So you have square root appearing, sines and thetas, and cosines appearing. So what's important to know, how do we take this submatrix and go to a different basis? So taking linear combinations of operators can be achieved by taking linear combinations of the couplings, or rather rotating your couplings. So if your couplings in your old basis are related to your couplings in your new basis by such a rotation matrix, then the anomalous dimensions in your new basis are given by such a transformation on your old anomalous dimensions. So this transformation I'm going to do into this new basis. And if we do this, indeed, as expected, what we find is that this submatrix becomes symmetric. If you see, this entry here is exactly the same as that entry. So this confirms the existing results, and or this exemplifies that. And here, in the next slide, in my final slide, I want to show it's basically the proof given in the CFT literature, but in a language that is perhaps more familiar for ineffective field theory, based on this Scott method to obtain anomalous dimensions. So just to recall, you can obtain your anomalous dimensions of your operators by calculating at 1 loop, by calculating such a 1 loop cut diagram. And this then gives, basically your operators multiplied by anomalous dimensions. So if we assume orthonormality, if we assume that we have an orthonormal basis, we can make use of this by, if you like, diagrammatically gluing on the right-hand side such the right-hand side of this diagram, so that here we obtain a delta jk if we do this with an operator k. So this isolates the anomalous dimension entry ki. And on the left-hand side, what we generate in this way is this very symmetric-looking diagram. So again, taking the phase space integral on this line gives you the second line, where now the anomalous dimensions are given by this symmetric matrix, and from this it directly follows that your anomalous dimensions are symmetric under interchanging I and k. So this submatrix becomes symmetric, or this shows that this submatrix is symmetric if we assume orthonormality with respect to the phase space integral. Now, one more step is required to go from this result, where we have a non-zero inflowing P, to the effective field theory, which makes use of this statement that the primaries are orthogonal to operators proportional to P. So if you want to have a statement on your physical anomalous dimensions, what you need to do is choose for your non-physical operators proportional to P, and then your orthonormality assumption will necessarily make your physical basis these primary operators. So the statement then is the submatrix of a physical anomalous dimensions is symmetric if the conformal primary part is orthonormal. So that is the result that we have confirmed in our calculations. So this brings me to the conclusion. So this was, I should have said before already, the first application of the R-star operation in effective field theory. And I've shown you some useful properties why it's useful, especially in effective field theory, where we obtain high degree of divergence and high loop order. So I've shown you the general structure, and I should say that some open questions remain, which are this 1 loop 0 only in the primaries and this 3 loop zeros, which are, of course, we show it by calculations, but before the calculations, they're unexpected. So thank you very much, and I'm happy to answer some questions if there are any.
Any questions from the room? Question from the online? Oh, Mike, go ahead.
Could you go back to page 6?
Sure. Oh, yes.
It just, I want to make sure I understood the comment you were making there.
Here, okay.
So it just, is the message the following, that the R-star operation is just a clever trick to basically pull out the divergences? It's not that you're saying that you're using this R-star operation to force the overall UV divergence to be local, right? Which always has to be true in any scheme, in general grounds, right?
Yes, yes.
Oh,
that's
okay.
Correct. That's
all right.
Correct.
Just the way you said it, I thought I wasn't quite sure what you were saying. Okay.
Okay, I'm sorry. Okay.
Okay, thanks.
So let me just say, so it's just, there's another operation called the R operator, which is just basically if you want to organize your renormalization, which is more familiar perhaps, which is just recursively subtracting all your UV divergences. This is what you also always do. R star is just a slight generalization where it also subtracts infrared divergences, but it's essentially the same.
Yeah, I think it just was the way you said it. I had the option to misunderstand. Thanks for the clarification.
Thank you for making me clarify.
Any other questions?
I have a question. May I? I mean, it's a very basic one. So you applying your technique to a scalar theory. How complicated would it be to apply it to something more similar to the standard model effective field theory with gauge bosons and fermions also?
Are you asking particularly about this R star operation?
Yeah, the whole chain of tools.
So, okay, thank you. So the R star operation, I mean, as a theoretical object, it's basically also suited for any theory. You can organize your calculation in this way. The code, however, is not yet ready for dealing with fermions. So I mean, so this is a practical step that holds us back a little bit. If you want to observe what we did, like the properties of the conformal basis, you can use existing results. The anomalous dimensions of the SMEFT are known at 1 loop, and you can just make this change of basis to observe its properties. But yeah, to go to higher loops, you would need something like R star. I hope that answers.
So you have problems with fermions, but gauge bosons are fine?
Actually, yes, I believe so.
So you could go to higher loops in the bosonic sector of SMEFT.
Yeah, I would say
that would be interesting. Thanks. Have a nice talk too.
Okay, we have another question from the conference room.
I have a question. You subtract both UV divergence and IR divergence using counter term, right?
So as I should have made maybe more clear, the counter terms are not really necessary. So as in this point, I say no explicit counter terms for subdivergence is necessary. You recognize them and you just subtract them, but you don't need to have them as vertices or in your Lagrangian anything.
And we know that IR divergence should be cancelled in the theory, if the theory is good, right?
Yes. Thank you.
So how do you cancel the IR divergence?
Okay, thank you. Very good. Very good. Thank you. So the issue is that we start with off-shell Green's functions. So these do not have any infrared divergences. The only infrared divergences that appear are because we manipulate these infrared parameters. So we play around, we do this infrared rearrangement, and we Taylor expand. This is what generates them, so that we know that they are non-physical. They are of another character than those infrared divergences that appear in physical processes. And that's why we really just want to remove them. And this is what R star can do for us. Does that clarify?
Okay, thank you.
Thank you. Thank you for your question.
So, yeah, in the interest of time, let's move on to the next speaker. Roberto, are you online?
Thank you.
Can you hear me?
Roberto? Okay. No?
Can you hear me?
I can hear you, but I can't see you. Can you share your screen?
Yes, sure.